Logarithmic and exponential functions revisited. Let's take a look back at all, or at least most, of the calculus we've learned involving logarithmic and exponential functions. One thing that we can now do is define e using a limit. So we have our limit definition of e. The limit as n goes to infinity of the quantity 1 plus 1 over n to the n power. Right, so we could think of this, we say e equals this, but we could also define e as this and use like a triple equal there, saying this is what e is. And it's fun to try this with different values on the calculator, right? You can always get e on your calculator by doing e to the 1. And then compare that with what happens when you plug in, say, 1,000 or 1,000,000 for these n values, and see how it gets closer and closer to the actual value of e, 2.71828. We can never say what e is, right? We'd have to keep rambling on decimals for eternity, but you can see this limit getting closer and closer to e. A more visual way to look at it might be to graph, and in fact we'll do this, graph f of x, the function, f of x equals 1 plus 1 over x, all raised to the x power. Let's graph this in Desmos along with the line y equals e, and show that as this goes off to, as we let x go off to infinity, this function approaches e. Okay, so I've graphed the curve y equals the quantity 1 plus 1 over x to the x power. That's in red here. And also the line, the horizontal line, y equals e. And you can see this red, so the y equals e is dashed in blue. So this is right at e here. We can see if we zoom in, we're about 2.71828, right? So that's our line e. And you can see the red line, the curve, approaches the dashed blue line as we go out to infinity, right? We could just keep going and going. But of course it eventually approaches it because this limit approaches e. So we can see that's a nice approximation for e, and as we let it go all the way to infinity, we'd have a definition of e. Now you may be saying, that's circular reasoning. You're using e to talk about a function that approaches e, and it's true, it's circular reasoning, but it's just helping us grasp the fact that indeed this limit does approach e. If we didn't know what e was, we'd just say it approaches some number, and we put that dash line in anyway and say, let's call this thing e. So that's how that's working. Okay, let's review some derivatives. Here are all the exponential and logarithmic derivatives that we've learned. Recall that we have the derivative d by dx of e to the u is e to the u prime. So I'm doing this in the chain rule form. Of course, the derivative of e to the x would just be e to the x, but we're going to use u to keep it as general as possible. So everything will have this u prime tagged on to remind us to, take the derivative of the inside, so to speak. Okay, the derivative of b to the u for any base is similar to that. Is b to the u prime, so same thing, except for we tack on a natural log b to the front. All right, d by dx of natural log of u, 1 over u, and then don't forget the u prime. Chain rule there. Same thing for natural log absolute value of u. We again get 1 over u prime. Okay, well the derivative of log base b of u, d by dx of log base b of u, is similar. We again get 1 over u prime, except for now we have a natural log b down in the denominator as well. So 1 over u natural log b u prime. And the same thing with the absolute value. We get d by dx of log base b of absolute value of u is 1 over u prime again, and natural log b, exact same derivative. Natural log b down in the denominator, that is. We mostly call out these absolute value cases. It seems weird to suddenly be talking about that, but it's so that when we do the integral of 1 over u, we know it's natural log absolute value of u, or x is what we usually see it as. There's no chain rule for integration, unfortunately. Okay, let's take a look at some integrals. Okay, for integrals, and we'll do the indefinite forms here, we have the integral of e to the x dx is e to the x plus c. Similarly, the integral of b to the x is b to the x plus c, except for now we're dividing b to the x by natural log b. So you can kind of remember it as when you take the derivative, you multiply by natural log b, but when you take the integral of b to the x, you divide by natural log of b. And we have that the integral of 1 over x dx is natural log of absolute value of x plus c. Now, I don't know if you've noticed this. We don't have an integral for natural log of x. Have you noticed that? That's never come up. We've conveniently left that behind. What's the integral of natural log x? We don't know. Same thing with log base b of x dx. We don't know. Turns out we need to wait until Calc 2 to get those. We use a method called integration by parts, but we'll need to wait a little bit on those two integrals